Okay. All right. So good afternoon, everyone. Today, the Atom Seminar has the great pleasure of welcoming Dr. Ian Bell. Dr. Bell received his bachelor's in mechanical engineering at Cornell University and received his PhD at Purdue University. Nowadays, he's a mechanical engineer at the National Institute of Standards and Technology. Dr. Bell's research interests include computational routines and tools used for the development and application of thermodynamic mixture models. These mixture models are used in software tools like RefProp, a modeling tool widely used in industry. In the last few years, Dr. Bell has been involved in several open source software projects, and he is also involved in the development of algorithms for mixture calculations. In this category, there are algorithms for the calculation of all the critical points for mixtures, phase envelopes, cross-sections, and robust and efficient algorithms for calculating density values from multi-parameter equations of state. So once again, welcome Dr. Yobel. Thank you so much for being here with us, and please feel free to start your presentation.
Thank you for the kind introduction. As was mentioned, I'm Ian Bell, and I come from NIST. And today we're going to be talking about residual entropy. So I titled today's talk, Molecular Insights Gleaned from Residual Entropy. And so what we're going to be talking about is, what is residual entropy? What does it teach you? And what applications can you make of the knowledge that you've gained? So an overview. First, a little bit of motivation. Why am I interested in this topic in the first place? Some background on the work, followed by discussion of entropy scaling, then some new work on crossover, defining a new liquid vapor demarcation in the critical region, and then applying this techniques to some real fluids, and then some closing remarks. And I hope to have plenty of time for questions at the end. So if you could please hold your questions until I'm finished, that would be great. So first, motivation. So if we look at the surface for viscosity for a fluid, let's say this is the viscosity data for propane, for instance. We have experimental data, which has dependence on both temperature and density. And when you're trying to fit an empirical model to data such as this, it's a challenging task because you need to find an empirical function which would like to represent this experimental data, and it's hard to do that if you're not guided by theory to some extent. So what we would like is to find a way to take this complicated three-dimensional surface and turn it into a two-dimensional surface. And that is the technique that I will generally be talking about today. And the advantage of this is now it's much easier to fit a function that is dependent on one independent variable than on one that's dependent on two. It's a much more straightforward exercise. And so when we want to make for instance, a viscosity correlation for propane, it's much easier when you only have one variable that you need to fit. So generally, that's the point of entry for me into entropy scaling. I wanted a way to develop transport property correlations that were very easy to develop and were nicely formed. So generally, the really big question that I want to touch today is, how are transport and equilibrium properties related? So I'm not going to answer that question, but this is a really fundamental question. So transport properties in general, the net transport of mass, momentum, or energy, so self-diffusion, viscosity, and thermal conductivity, requires a gradient of some kind. And thermodynamics is, in our most general thinking about thermodynamics, is mostly about equilibrium. So one could say that to first order, we should not expect, in principle, any link between thermodynamics and transport because they're fundamentally different. But there are formalisms like Green-Kubo and Einstein approaches that link autocorrelation in equilibrium systems and transport. So the goal today is to show how the residual, or sometimes called the excess entropy, captures elements that are essential to understanding transport and also thermodynamic properties. So first, some background. If we go back in time a few decades, we end up at the work of Yakov Rosenfeld. And really the way before its time idea that Rosenfeld had is that the scaled transport properties, here scaled self-diffusion and scaled viscosity, can be very well represented as a monovariate function of an entropy term. So he called it the internal energy. That same term is now called either the excess entropy or residual entropy, depending on the community. So the key point to mention from Rosenfeld's work is that you have a scaled transport property in the liquid phase in particular that is one-to-one with a thermodynamic quantity. That is, if you know the transport property, you know the thermodynamic property. If you know the thermodynamic property, you know the transport property. So what this suggests, therefore, is that there is some connection, although we don't know what the form of that connection is, between the thermodynamics and the transport properties. But we don't know the functional relationship. Here it looks like it's exponential, and we'll talk on what exactly is this functional relationship. But all we can say at this point is that the functional relationship is monovariate, so it's a one-to-one relationship. Scaling experimental data or modeling data also in this way has come to be called entropy scaling. Sometimes it's called residual entropy scaling, but really anyone who's experimenting in this field, the work is tied back to what Rosenfeld was working on in 1977. This is an idea that languished in obscurity for several decades, and really only after Rosenfeld's death did this concept of entropy scaling really enter the, let's call it, mainstream. So in this entropy scaling approach, the transport properties are non-dimensionalized by the appropriate mass, length, and time in the liquid phase. So you have tilde eta. So tilde properties in this work are always going to be macroscopically scaled. So tilde eta is eta divided by the number density to the 2/3 and the square root of mkbt, where rho n is the number density, m is the mass of one particle, kb is Boltzmann constant, and T is the temperature. So the definition that I'm starting from for what I'm calling the residual entropy, and you'll notice throughout the talk that there are some slides that have residual entropy and some slides that have excess entropy and some slides that have S+, but they're all completely synonymous. So what I'm talking about is residual entropy in here, which is the entropy at a given temperature and density minus the ideal gas at the same temperature and density. I'd like you to note, importantly, that this is not at the same temperature and pressure. There is a factor of difference of the gas constant times the logarithm of the compressibility factor difference when you use Tp and T rho as your independent variables. This is sometimes called the excess or configurational or internal entropies, but they're all the same thing. And so this point is a point of confusion in the literature about what should you call this quantity. What this term actually means is that the residual entropy is a reduction in entropy caused by molecular interactions. These interactions are both attractive and repulsive interactions. Both attractive and repulsive interactions they impact the entropy in, it's always negative. Residual entropy, as I write here, is always negative. And that is unique among residual properties. That's not the case for residual internal energy or residual Gibbs energy or other properties. So there's something special about the residual entropy. Now, dilute gases have the highest entropies. We can say they have the most accessible microstates. So if you think about Boltzmann, you can say that entropy is kb ln accessible microstates if all the states are equally probable. And the structure of the fluid is synonymous with the residual entropy because the accessible microstates are removed by interactions, both repulsive and attractive. And so that is why the residual entropy is always negative. So I personally like to define this term S+, which is defined as negative of SR over KB. So this is a measure of the structure. The more positive it is, the more structured the phase is. This is, I'd note, the same variable that Rosenfeld used in the slide that I showed you before. So this quantity S+ can be evaluated from an equation of state. So if you have a compressibility factor as a function of temperature and density, you can integrate that to get the residual Helmholtz energy, and then you can take that temperature derivative to get you S+. or other ways to get S plus. You can use Witten insertion or thermodynamic integration or a number of other methods. But the key point that I'd like to highlight is that this quantity S plus, or residual entropy, is something that is obtainable both from simulations and for real species. And this is really something that is quite different than a lot of other approaches that are proposed either for that are really only applicable to molecular simulation or are only applicable to, let's say, real fluids. And one thing that's neat about the residual entropy is that it bridges these two worlds, and it allows you to, in a straightforward fashion, connect real systems and molecular systems that are only accessible in simulation. Now, one might reasonably ask, well, what do the contours of residual entropy look like for a real fluid? And here I'm showing an example for CO2. So these are contours of residual entropy for CO2 at zero density. The residual entropy is 0 because there's no reduction in microstates caused by interactions. And that's true for all temperatures. And then as you increase in density, you can see that there is more or less a monotonic increase in the residual entropy, or in S plus, which is here, the negatives are becoming more negative. And you head ultimately to this red curve, which is the melting line, which is itself approximately a curve of constant residual entropy. So this is, again, the VLE here, and then this is the melting curve. And so dilute gas would be here in the limit of zero density. So the van der Waals equation gives us some insight into the residual entropy. So the residual entropy itself includes the effects of both attraction and repulsion. So if we look at a very simple case that we like to think about all the time, and look at the van der Waals equation, which is the difference of a pressure contribution coming from repulsion and a pressure contribution coming from attraction. Now, if you take that equation of state and you integrate it to get residual Helmholtz energy and then differentiate to get the entropy, you get an S plus value, which is minus the log of 1 minus an eighth kBT at the critical point over the pressure at the critical point times the number density. And what I'll just tell you, it's maybe not so obvious here, is that if A is constant, S plus only comes from the repulsive part. So the attraction part doesn't factor in at all to the residual entropy that you obtain from the van der Waals equation of state. And so what this is telling us is that in this case, the van der Waals equation of state is suggesting that the value of S plus is largely governed by repulsion. And this is a common theme that we'll be touching on in this talk. The transport properties are also strongly governed by repulsion. So entropy scaling is an exact solution for some systems. So in that class would be hard sphere and inverse power law fluids. So in the inverse power law fluids, you have a potential which is proportional to the separation to a power negative n. And so for this particular fluid, there is a single thermodynamic variable, which is called capital gamma, which is the density to the n over 3 divided by t. Therefore, you can write the S plus as a function of gamma. And similarly, you also get scaled transport properties that are a function only of gamma. So from a functional standpoint, one could think about the fact that the macroscopically scaled viscosity is also a function of S plus. One could, of course, also say that it's equally a function of gamma. Now, this relationship, what they call so-called entropy scaling relationship, this monovariability, holds over the entire phase diagram for the inverse power law, all the way from zero density limit to the melting curve. Now, the question that I'd like to ask is this representative of real fluid behavior for species that we might actually want to measure in our labs or simulate in our computers? So it must be said that the entropy scaling approach is only an approximate solution for real systems with more complex interactions than those of inverse power laws or completely hard interactions. But as we'll see, it's a very good approximation for many fluids. And even when it isn't for the entire phase diagram, it often is a very good approximation for much of the phase diagram. So there's a really nice review from Yepadira covering the work in what we call entropy scaling up to the year 2018. And so I would definitely recommend anyone who's interested to take a thorough read of his review. Now, one of the limits that is identified in the entropy scaling approach is that you can't have hydrogen bonding or directional bonding, so water is out. And there are a lot of very simple model potentials, Gaussian kinds of models that show counterexamples where entropy scaling does not work. And sometimes we find that it works better than you should expect, and the monovariability is more monovariate than you would expect, but not always. So now we're going to talk a little bit more about entropy scaling in general. And again, I want to highlight the point that I'm most interested in is theory in the service of solving practical problems. And in this case, the practical problem is how should one develop empirical correlations for transport properties of technically relevant fluids. And so the vision here is we want to minimize the experimental measurements that are needed. So we also do measurements in our group, and those are expensive time-wise. And so we want to do as few measurements as possible. The other part of the vision is to simplify the empirical formulations used and make the processes less opaque. So the processes used to develop these correlations are very straightforward, conventional, linear optimization problems. So first, we're going to start simple to develop an understanding of what is going on. And to do so, we're going to focus on our friend, Mr. Leonard Jones. And so the Leonard-Jones model is used in many systems, in many domains of research to understand the delicate interaction of attraction and repulsion on the behavior of fluids. It's perhaps the most well-studied model potential. And in our paper from 2019, we collected all of the simulation data for Leonard-Jones. It's available in the literature. We used a very accurate equation of state to calculate the residual, or in this case, excess entropy. And we plotted all those points in the Rosenfeld scaling diagram. And so in fact, this is the same figure that Rosenfeld put together, but with many more data points. And so what you can see is that Rosenfeld's initial supposition seems to be basically true, that in the liquid phase particularly, so I can tell you that's from approximately 1 to 3.5 is the liquid phase for the residual entropy for the case of Leonard-Jones. And beyond 3.5 or so, we have a supercooled phase. You have a very close to monovariate relationship, and some of these data points that you see being slightly off of them, we believe to be deficient data points themselves. And as a point of orientation, the critical point is around 0.85 in these coordinates for S+, which is synonymous with this negative SEX over KB. Now, one thing that is very interesting about this entropy scaling approach is that it also applies to the very supercooled phases. So in 2020, we looked at model glass formers, including Cobb-Anderson. And when you do the same basic exercise for these more supercooled systems, what you see is the same basic behavior that you have in liquids, where you have this monovariate relationship between the scaled transport property and S+, also holds more or less as you get to very, very supercooled states. For other systems which are more complex, they're not just single component systems anymore. So, and why does this work in fact? So if we go to the theory a little bit, so the point here is to talk about isomorph theory, which is, one can say, the observation that when the fluid is strongly correlating in the canonical or NVT ensemble, certain properties are constant along curves of constant structure. I'm trying to not get too into the weeds here. So the key point that comes out of that theory is that both the scaled transport property and S+ are included in this set of properties that should be constant along these curves of invariance. So isomorph theory predicts that tilde eta should be a function of S+ under the correct set of conditions. And so the conditions are based on the Pearson correlation R between the virial of the potential of the ensemble and W, the virial of the ensemble, and U, the potential of the ensemble. And so you calculate the Pearson correlation R, and when this Pearson correlation R is greater than 0.9, this is a sufficient but not necessary condition for entropy scaling to apply. And highlight again that this is a quantity that is accessible in simulations and is really only an inference for real fluids. Then in this figure, as shown from our paper, we look at where is the value of R greater than 0.9 in the temperature density plane. And so again, VLE liquidus curve along here. And you can see that in the liquid phase, there's a big portion of the domain, the big triangles, which are points that have R greater than 0.9. And even you can see down into the gas region, if you go high enough in temperature, so several times the critical temperature, you again have these values of R, these triangles that are greater than 0.9. So it's a good portion of the phase diagram that we can explain by the isomorph theory why this entropy scaling approach works, in particular for monomers, but also for more complex molecules. So if you go back to this figure, you can see that there is this very annoying hooking behavior as you go towards zero density. And the reason for that is that in the denominator of the scaling approach, you have this density to the 2/3 power. And as you go towards zero, this is a pole, and therefore you get divergence in the scaled viscosity, which is something that Rosenfeld didn't have to worry about because the simulations were in the liquid phase. But in general, there are data for Lennard-Jones covering the entire phase diagram, and there are collision integrals in the limit of zero density, which are useful. So in my paper from 2019, I sort of, let's say by accident, figured out that if I were to multiply the tilde eta by s plus to the 2/3, then you take the divergence away. And so now you have a little bump over here, which we'll talk about, but you no longer have the divergence. And sort of magically, once you do this scaling, you multiply by s plus to the 2/3, now you have an almost perfectly exponential relationship for basically the entire liquid phase. And then you'll note there's a little hooking behavior when we get up here. It's subtle, but it's there. So from this curve, you end up with eta plus. So this modified residual entropy scaling quantity as a function of s plus. You can say that it's 0.2163 times the exponential of basically 1.0 times s plus. So the relationship is almost exponential between these two quantities. So the way that I like to describe this, and I'm abusing the vocabulary a little bit, I call this a Arrhenius region for the linear relationship, and then a super exponential or super Arrhenius region when you get into the supercooled liquid above approximately 3.5 in these coordinates. And Lennard-Jones is not particularly special in this regard. Larger molecules are like this too. So if you look at propane, you have an Arrhenius region, and then you have a super Arrhenius region that picks up after the Arrhenius region ends. And I don't have time to talk about propane in this work, but there's a paper from 2020 that looks at propane in great detail and looks at some of these questions about the Arrhenius and super Arrhenius behaviors. So the dilute gas limit. So why does this work? The virial equation of state is given by our familiar friend z equals 1 plus the infinite summation of the virial coefficients times the density to the n minus 1. If you then take this and you integrate to get alpha r or ar, and then differentiate to get s plus, and you end up with this formulation. And if you take the zero density limit of the derivative of s plus with respect to density, you get b2 plus t db2 dt. And so what that means is that the limit of eta plus in the limit of rho going to 0 is now the zero density limit of the viscosity divided by square root of n kbt times b2 plus t db2 dt to the 2/3. So that's, again, this 2/3 power is coming from the s plus to the 2/3. And you end up with a values for in the dilute limit, which are approximately on the same order. So you have values that go from 0.2 to 0.24 something up to 0.236, 0.36-ish. And what's interesting is that at infinite temperature, you're approaching the n equals 12 value for an inverse power law. The inverse power laws have a fixed value for all temperatures in the zero density limit in these coordinates. And again, there's a paper in JCED that goes in detail looking into this dilute gas limit. So to reiterate, for Lennard-Jones, residual entropy is very strongly correlated with the scale of viscosity over almost the entire phase diagram, even sometimes when R is much less than 0.9. And the functional relationship between eta plus and S plus merits further theoretical investigation. It seems unlikely that it's a complete coincidence that the value is completely almost exponential. And as I mentioned here, the dilute limit of the scaling has been studied in a paper in 2019. And I'm talking here about viscosity, but many of the same arguments apply also to self-diffusion and thermal conductivity. You, again, in the case of self-diffusion, need to worry about the zero density limit. In the case of thermal conductivity, you need to worry about critical enhancement. But away from these places, the same arguments apply. So now I'm going to take a slight diversion and talk about crossover. And so the theme here is, what is it that separates a liquid phase from a gas phase in supercritical region? And in order to look into this question a little bit, we're going to come back to looking at model potentials in a little bit more detail. So here I've plotted data from the paper in 2019, where I looked at a number of different model potentials. So WCA, Lennard-Jones, inverse power law, and hard sphere, and overlaid the results for all of the fluids in the same figure. And so one thing that you see that's intriguing is they qualitatively all look roughly similar, but more so than that, they all seem to have minima that are at approximately the same value of S plus or negative SR over R. And that's interesting. And the value is approximately 2/3, I'll just tell you. So there's a clear consistency in the location of the minima in scaled viscosity. So why might that be? First, we looked at this in the entropy scaling framework, looking at the minima of tilde eta. But one thing that we identified, and that reviewers of our paper identified, is that the minima of tilde eta don't go through the critical point. And we had to agree with the reviewers that this was an unsatisfying conclusion, that it makes sense for a liquid vapor demarcation to pass through the critical point, because that is sort of our fundamental understanding of what makes fluids different. But the values are all, as I said, at approximately a value of 2/3, which is an interesting and nice, simple value. And so, as with many things in this general exploration of residual entropy and entropy scaling, there are a lot of just beautiful results that fall out, but it's not always so easy to explain why these beautiful results are falling out. And I'll touch on this at the end. So we took a slightly different tack, which is to look at the individual contributions to the viscosity, the kinetic and configurational parts in molecular dynamics simulations. So I'm sorry, I understand there's quite a lot going on in this figure. There's a larger version in the paper, but first I want to draw your attention to the fact that on the upper part of the figure in the gray shaded region are kinematic viscosities as a function of temperature in color and density in the x-axis. And on the bottom part are the configurational and kinetic contributions relative to the total viscosity. For Lennard-Jones is the markers, and then the curves are the hard sphere from Enskog theory. And what you note is that on the upper figure, the minima of the kinematic viscosity have a strong temperature dependent, strong density dependence. And the observation from our work was what happens when you change your mental model and you think about these quantities rather than being a function of density, but being a function of residual entropy. And an absolutely beautiful result falls out of that, which is that the location of the minima of the kinematic viscosity all occur at the same value of residual entropy, where the configurational and kinetic contributions to the viscosity are equal to each other. And as you can see here, the minima of these curves, of course, there's some scatter from the noise in the simulations, but the overall conclusion is clear that there is something that these two things are linked, because you end up with them crossing at the same value of residual entropy. So residual entropy is a way of making sense of the kinematic viscosity, which is a commonly considered metric for crossover between liquid-like and gas-like behavior when it comes to transport properties, in particular viscosity. And so this is a way of dealing with this question. So the point here is that the minima of eta over rho, or kinematic viscosity, is the same point where the configurational and kinetic contributions to viscosity are equal. This is itself an exact solution for the hard sphere from Enskog theory. You can show this with a little bit of algebra. And only when you make the independent variable S plus do you get the full collapse of all of these fractional contributions to viscosity and kinematic viscosity curves. And Leonard-Jones shows the same behavior as the hard sphere does, which is really important. So what you can take from that is that it's really all about repulsion. And that's a point that I made earlier on, and that's a point I'm going to make again. The curve for the points goes very close to the critical point of Leonard-Jones, and I'll show that on the next slide. And so what we have now is a new crossover curve between supercritical liquid and gas phases that is accessible in both simulations and experiments. So you can calculate this curve up to essentially as high in temperature as you would like to go. This is to be a distinction from things like the Whittam curve, which terminates at a temperature not so far above the critical temperature of the fluid. And here is a plot of this curve that goes through the critical point, and the points in the temperature density plane of the points where the kinematic and configurational contributions are the same, and where the minimum of the kinematic viscosity are. And so you can see that for the monomer, so n equals 1, that there's a very good agreement in the locations of these points for the x's and the o's. And for the dimer, that's still the case. For the dimer, you still have very good agreement in the locations of the points. But then you have this curve here, which is the one coming from the critical point, is quite different than the curve where you have the equality of the kinematic viscosity of the viscosity contributions and the minimum of the viscosity. So there's something going on here that we don't fully understand here, and why that works for the monomer and not so much for the dimer. So for brevity, I'm going to, I think, skip this slide and get into the real fluids a little bit. So in the paper in 2019, I collected the most accurate data for 8 important fluids. So argon, methane, CO2, sulfur hexafluoride, 2 halogenated hydrocarbons that are refrigerants, so they are numbers, and water and methanol. And what you can see, the data are stacked by powers of 10 so that you can clearly see the data separate. One interesting thing is that they all look qualitatively similar. You have this divergence problem as before with the Rosenfeld scaling. You have a minimum in the curve, which moves its location. You have something like exponential behavior. This curve is the curve that Rosenfeld used to fit his data. And so you can see that as you get further and further away from, let's call them simple systems, although I know a lot of people don't like that term, but simple system like argon, which doesn't have any sort of association to worry about, Then as you go towards water, you get further and further away from the curve that Rosenfeld proposed. And I want to talk a little bit more about water. So water is a tricky case when it comes to entropy scaling. There are copious high quality data for this fluid. Entropy scaling actually works pretty well over part of the phase diagram. If we go back, you can see that there's a really good agreement of the data in this region. There's close to a monovariate relationship, but down here, it's difficult to make out in the scale of this figure, but the monovariability is very poor. And also that's the case in the deeply supercooled region. And you really need all of the experimental data to see the deficiencies. If you only have access to a subsection of the data, for instance, what is available in some of the commercial property experimental data libraries, you don't get the full picture. You miss out on portions of this data in here, and you miss out on portions of the data in here. And it looks as though the curve is monovariable, but in fact, you are missing the full picture because you don't have the right experimental data that you're looking at. And another thing to talk about here is the dilute scaling approach. So from let's say like 2011 to maybe like the latter part, like 2018 or so, pretty much everyone who's tried to do practical applications of entropy scaling have, rather than applying the plus scaling that I propose, they've divided by the dilute gas viscosity. And this has a very natural feeling, like it is straightforward to understand why this is appealing. But the problem with this approach is that it uses the wrong length scale in the liquid phase in particular. So isomorph theory, so if you want to say that I'm developing a method that's based on isomorph theory, you need to use the right length scale. And isomorph theory requires you to use the number density to the -1/3. And that's not what you get when you divide by the dilute gas viscosity. And so here's a demonstration of why this is a bad idea. If you take the viscosity and divide by the dilute gas viscosity, in this case for argon, which is a simple monatomic gas, monatomic fluid at least, in the liquid phase, so this is, the critical point is around here. So if we're in the liquid phase here, you can see that there's a very wide band in this scaled viscosity in this way, and that's not present when you use the plus scaling. So the solution is to use plus scaling and instead to subtract off the dilute gas contribution. It has the same net effect as dividing by the dilute gas viscosity, and is much better behaved in the liquid phase, particularly for small molecules like argon, methane, and things like that. So I've done a lot of talking about simpler systems, but now I want to really briefly touch on some of the more practical applications that we're looking at. So in recent years, there's been a lot of interest in refrigerants. I mean, the people have been looking at refrigerants for decades, but in recent years, been looking at new refrigerants, like halogenated olefins in particular. And so one of the things that my collaborator and I did is to rescale the entropies by this scaling parameter psi. And you can identify that there is a relationship between psi and the value of S plus at the critical point. And that's important because when you apply this scaling, so we take the S eta plus, subtract off the dilute gas contribution and add 1, when you plot that as a function of S plus divided by psi, then you get collapse of essentially all of the viscosity data for all of the refrigerants. And so that allows us to develop a quite accurate estimation scheme for refrigerant viscosities based on this approach. And so the other properties, things like thermal conductivity, have a very similar behavior. Of course, there are complications like critical enhancement and internal degrees of freedom, but fundamentally, thermal conductivity should follow the same rules as viscosity when it comes to isomorph theory and entropy scaling in general. I think at this point, we can say that it is expected that entropy scaling should apply for all non-associating non-quantum fluids. there is a problem in the extended critical region. As you get closer and closer to the critical point, the value of R, this correlation factor, goes towards 0, and it's unclear what to do about that region in particular. But we can still make use of very accurate first principles dilute gas calculations for small rigid molecules, so we can still take advantage of the things that we know the most accurately. So finally, I have some closing remarks, and then the floor will be open for questions. So to conclude, I'd like to say that entropy scaling puts the emphasis on repulsive interactions between molecules. The fully repulsive model systems, here I've talked about inverse power law, I've talked about hard spheres. They're really a lot like real fluids in the entropy scaling framework. And this allows you to do a relatively straightforward mapping to fluids without having to fit parameters, like normally for Lennard-Jones one would have to fit the epsilon and sigma parameters, but you don't have to do that when you use entropy scaling, because the macroscopic scaling sort of bakes in these microscopic scaling parameters. Entropy scaling offers the promise of highly accurate empirical models, mostly dependent on S+. And this crossover that I mentioned between sort of liquid behavior and gas behavior appears to play a key role in harmonizing the entropy scaling. And so what you end up with is a new flavor of corresponding states. So this extended corresponding states has been around for a long time and has really been very successful. And this is sort of the next generation of that overall approach, I would say. But I've been working in this field for a number of years, and there are a lot of interesting questions that have come up. And so I think I'm going to close my talk with a list of things that I'm interested in this field that I don't know the answers to. And here we go. So what should you do about mixtures? There's been some empirical progress and various scaling rules, but there's opportunities to improve the theory of entropy scaling as pertains to mixtures. What should you do in general when isomorph theory fails for normal fluids in the extended critical region? There's a little bit of discussion of this in the propane paper and also in the krypton paper, but I don't know what the right solution is there. How can you make sense of the crossover results for polyatomic species? Is there something about the internal flexibility or internal degrees of freedom that gives you a different answer in terms of what part of the entropy is most relevant? More fundamentally, is there a unified theory of entropy scaling hiding somewhere? And I ask that question because in many cases, entropy scaling works well when by rights it really shouldn't. Practically, it's important for us to figure out how to correct for fluids when the hydrogen bonding causes a breakdown in the scaling. So for instance, most especially water. So it would be really nice to apply entropy scaling to water, but so far, I would say nobody's had great success with that. How do the quantum effects impact residual entropy and the scaling? This is relevant when you get down to cryogenic temperatures. Why is the Arrhenius super Arrhenius crossover so uniform in terms of S+? I didn't really touch on that in this talk, but the paper looking at alkanes and also on propane talk about this question. And I think there's something very interesting to be learned thinking about this Arrhenius super Arrhenius crossover. And also, why are the minima of tilde eta for monomers at S+ of 2/3? It's weird. So with that, I'd like to thank you all for your attention, even virtually, and ask if there are any questions.
Okay, Dr. Ian Bell, thank you so much for the presentation. We are now open to questions. If you want to participate, please enable your microphone or write it down at the chat and we will read it. Also, our YouTube viewers can write it down too. So who is going to be the first? Professor Fred, okay.
I can be the first. Thank you, Ian, for this nice presentation. I'd like to ask you about how you compare this method with all the methods that we're using for viscosity, like free volume theory?
That's an excellent. So, sorry, continue your question. I'm trying to get out of full screen mode. 1 second.
No, that's all how we compare, and if you think that this method is going to be like engineer approach for the next year, because I do like this method, but some like Richard Elliott, I don't know if he's here. He doesn't like much, but I don't know.
So I would say that that in fact one need not pick between free volume and residual entropy approaches, because in a sense, free volume is the residual entropy. They are the same quantity in a way, because they're actually, the way that you can calculate residual entropy is by insertions, and insertions are essentially testing the free volume in the system. And so I think that's one thing that's really appealing about the residual entropy approach, is that it brings together, it merges a lot of the existing approaches that we use for modeling transport properties and gives them a more rigorous theoretical background. Even if the theory does not exactly apply in a lot of these practical systems, it gives you a more stable footing to start from. But thank you for your question, Matt. That's a good one.
Thank you. I have tried another scaling, like free energy scaling.
Yeah.
You know that because you comment about this paper. And I thought it was interesting, and even though the formulation is not so rigorous,
yeah,
our result was exciting, you know,
yeah,
even for water or for polar systems. Unfortunately, we didn't continue this project because, well, so some of his reasons. But I'd like to continue this approach to test and compare with entropy scaling.
Yeah.
Can you comment that?
So I guess the one comment that I have is that I'm happy to have people experimenting in this space. I think that thinking more broadly about what matters when it comes to linking transport and thermodynamic properties is great. I think the more ideas, the better. And the only comment that I have briefly is that I think that residual entropy is a more meaningful parameter when it comes to capturing the things that are relevant, because of the fact that it doesn't change sign, and you can really think about counting states, which is something that I think is hard to do when you think about residual Helmholtz energy. You can't build up this sort of mental models for what is going on so easily as you can with residual entropy, but maybe we need to expand our understanding, and that's the only limitation, is what we know. And so I would say don't give up, and I would be very interested to hear about what you discover.
Thank you.
So I think we have a question from Professor John O'Connell. Professor, feel free to enable your microphone and just do the question.
Hi, Ian. Thanks so much for a nice talk. And obviously there are both accomplishments in correlation as well as many questions left.
Yeah.
I don't know whether you know the name Mike Abbott, who worked with Hank Van Ness on thermodynamics textbooks and so forth, but he was working on equations of state, and his comment was about free volume. It said it took him a long time, but he finally figured out that free volume was entropy and drag.
Mm-hmm. Yeah. And if you put it exactly in those terms,
yeah,
you have viscosity, which is drag, with a little bit of hand waving, and then the entropy part. So and so I think that like what you're touching on is the fact that this residual entropy quantity suggests that there are these connections which have not really been explored in maybe the same, communities haven't overlapped enough to really transfer the ideas.
Yeah, there are two other questions that I might ask them. One is what is the effect of temperature relative to that of density? My impression is that density is really the dominant effect on transport properties, which of course, when you're at high density, like in a liquid phase, the repulsion, as you say, the repulsion is really what's going on, and attraction really is small. So it wasn't obvious to me how important temperature was in what you presented.
So I think the thing that's kind of neat and cool about the entropy scaling approach is that it brings in both of those pieces. So for instance, when you apply the scaling, you bring in a square root of mkbt term, which captures sort of the kinetic part, and then you have the packing part. They're sort of baked into this approach. So I mean, certainly the temperature matters, but I think, like, even if you just look at like what is impacting residual entropy, that is mostly driven by viscosity, or by density, not more so than by temperature. It's like the curves are like flattening, but they're still mostly moving over in density. Right. And it's complicated, but mostly it's density.
Yeah, well, again, that would go back to the fact that the free volume goes as density, pretty much.
Right.
The other question I have is, many years ago, we developed a corresponding states correlation for transport properties of molten salts.
Mm-hmm.
I don't know whether you ever saw that paper. It was 1973.
No. Okay.
Let me send it to you.
That would be great.
What we did was to show that previous theories had taken the melting temperature as the corresponding state, and of course that's foolish, because the solid phase is not corresponding even if the liquid phase is. So we chose a liquid phase state characterized by a particular property. And it worked like a charm for all of these properties of corresponding states, and it may also go along with what you're trying to do, which is develop a corresponding state for liquids.
Yeah, there's a lot of new literature on the topic that you raise, like this sort of corresponding states like approaches in liquids. And we actually are about to, or have submitted a paper on molten salts transport property scaling. So, but I didn't know about your paper, so I'd be happy to learn about that.
Yeah, I'll send it to you.
Thanks.
So João raised his hand, but for some reason he left the call.
Okay.
But I think we have a question from Guilherme Galeiro. So he has raised his hand. So please feel free to enable your microphone and ask the question yourself.
Okay, hi Jan. Thank you for this nice talk. It's really good to have an overview of all the application of this framework. It's really excellent. I have one question related to the work you did with the team of Eric May, where you try to make a generalized formulation. You said that your C factor is connected to the S plus at the critical point. There is a kind of link. Did you try to make it in the reverse way? So where you just draw this figure and using simply the S plus critical to scale your S plus, so as to check whether or not it's more or less general, at least in the first approximation for a wide range of system.
Yeah, I've tried variants on that theme, many variants on that theme. Generally, my experience has been that has not been super successful. I think the primary reason is because a lot of the critical point residual entropies are wrong from the equations of state. And a consequence, therefore, is that you scale things, but you scale them in the wrong direction. But what other teams have found is that by scaling by the wrong point, sometimes you get the right behavior again. Like even though it's wrong, everything is wrong in the same way, so that you still maintain consistency. And so I don't know, like it's not quite straightforward to me. I think what I saw with the alkanes is that it's somewhere between like the minimum that you want from the 2/3 and the critical point is somewhere in that range. And so generally that's true. And we have another paper that is like in preprint form, it's out now, and look at that question a little bit. I can send you the link. Again,
Okay.
from Dr. Yang. So and it works pretty well. And so there's clearly a link. It's maybe not perfect, but there is an empirical observation at the very least.
Okay, thank you.
João is here again in the audience. So João, I saw that you had raised your hand, so please feel free to make the question yourself.
Thank you, Maria, and thank you, Professor Yang, for the amazing presentation. Me and my colleagues we had doubts about the application of real fluids.
Mm-hmm.
When you talk about when density goes to zero, viscosity apparently doesn't follow, don't go to zero as well. And we were confusing why does that occur?
So maybe I need to clear up a point of confusion, because when we talk about zero density, we don't really mean exactly zero density. We mean two bodies in an infinite domain. Because what you, in the dilute gas limit, it's commonly called, that doesn't mean that it is one particle or zero particles in an infinite box, because that would be meaningless. There's nothing to talk about in that case. But what we really mean is two particles in a box. And the two particles are interacting with each other, and there's nothing else for all space. And that's the interesting piece, because that comes down to two-body interactions only. And so the nice thing about that is that you have techniques that you can use to calculate two-body interactions. So virial coefficients, for instance, can be calculated. And that's why I put up that slide talking about the dilute gas limit, because you can calculate those quantities relatively straightforwardly. I wouldn't say that it's straightforward, but relatively straightforwardly. And that teaches you a lot of interesting things about what real molecules do in that dilute limit. But you're right, it's not zero density, because that doesn't make sense. It is two-body in infinite domain density.
Thank you, Professor, for your explanation.
Sure.
So I think our time is almost over. So I want to thank everyone for the discussion. And once again, thank you, Dr. Ian Bell, for the presentation. So our seminars are being recorded and posted on YouTube, of course, after the invited lecturers agreement. Please check them out on our YouTube channel. This is our organization committee. We are responsible for inviting and communicating with the lecturers. We also handle social media, video editing, certificate writings, and hosting. Thank you all for being here today. We will meet again in 1 week, October 20th, and at the seminar that will be given by Professor John O'Connell, entitled the International Conference on Properties and Phase Equilibria for Product and Process Design. Please, Professor John O'Connell, I can see that you are in the audience. Please feel free to give us a brief description of your presentation.
I'm sorry, I didn't hear that.
So we have the presentation here. I think we can share for you.
Well, I can do it.
Oh, you can do it? Oh, okay.
Yep. I'll have to, let's see.
Take your time.
Do you see it?
I cannot see here.
All right,
Not yet.
let me share my screen.
Yeah,
Now it's coming.
yeah. Now we can
Okay.
see your presentation.
Okay, now you see it?
Yeah.
Yeah, but it's not in the presentation mode. So you can
Shift F5.
yeah.
Okay, now I have a problem. I've got two screens and only one shows. So let me try again.
I think you can go to slideshow.
Oh, well,
Or
interesting. It caused the slideshow on mine, but it doesn't on yours. So let's just leave it like this.
okay.
Okay, go ahead.
Anyhow, I'm an old guy in our profession. And so, in fact, some people will tell me that I'm history. So, Professor Tavares had asked me to give a history of thermodynamics, recent history, and I said, that's impossible in 40 minutes, but I can review what is evidence of the evolution of our community by the history of the PPE, PPD conferences, which every 3 years our community gets together to talk about the developments that are going on, learn some new things, as well as enjoy each other's company. This has been going on since 1977. I'm the only person who's been to all of 15 conferences over that period of time, and also been part of the organizing committee for all but 2 of the conferences. So I thought, and I also wrote a book about this, which carried through to the meeting in 2013, which was in Iguazu Falls, and shared by Professor Tavares along with Susanna Bettini from Argentina. So what I propose to do is to show you what's been developed, as well as include the update of the last 2 conferences. This shows the covers of my book, where these are the logos of all of the conferences from 77 to 2019. And here's the flags of the countries that it's been held in. So it's truly a global conference. The next one's coming up in May of next year. And one of the things I hope is to encourage any of you who could possibly make it to Spain and Tarragona to try to do that. Registration will be coming up soon. Thank you.
Thank you, Professor John O'Connell, for the brief description of your presentation that will be given next week. So thank you all for being here today.
Please, let I make a correction here about these flags. In 27, this conference was shared by Brazil and Argentina.
Say that again, Fred.
In 2027, the organization was shared from Brazil and Argentina.
No, this 2013. Yeah, so the Brazil flag should also be there, is what you're saying.
Yes.
Sorry about that. The problem is fitting. Tell me what pattern I should make to put the 2 of them together.
You could overlap them, like 1/3 overlapping of the 2.
Yeah, one way or another. Yeah.
Brazil can be on top just to satisfy Fred.
Okay, I will fix that. I will fix that. Thank you.
Okay.
Thank you, Professor Fred, for the little correction. So thank you all for being here today, and see you all next week.